Hey everyone, it's Bradley Bush with an algebra video. Today we're talking about systems of linear equations in three variables. And here's our to-do list. The first thing we're going to talk about is a quick overview of what systems are of linear equations in three variables, and then we'll talk about an example. This example will be a worked example, and it will be the type that has one solution. Over on the right-hand side, I just want to remind you that when we have systems of linear equations in three variables, then we are in three space. Let's start with our quick overview. So what exactly is a system of linear equations in three variables? Because it sounds kind of complicated. So let's first start with the three variables part. Well, that simply means that we just have three variables. We have equations, and those equations have three variables, usually an x, y, and a z. So that's not bad. Let's talk about the linear part. So linear equations. These equations, because they're linear, that means they follow the form ax plus by plus cz equals d, where the x, the y, and the z are the variables, and they all have an implied 1. So you don't generally see the 1, because if there is just a 1, it's implied and it's not written. But what you shouldn't see is a squared or a cubed or a 1/2. You shouldn't see anything. It just should be x, a y, and a z, or whatever three variables happen to be in your system. The a, b, c, and d, those are just constants. So because we're in three space, think of these as sheets of paper. They're actually planes in three space. So two-dimensional planes in three space. So a bunch of sheets of paper that touch. That's really what we're looking at. What does a system mean? Well, that just means you have more than one of them. So you have more than one sheet of paper or more than one plane. In our case here, we're going to have three sheets of paper or three equations that all represent two-dimensional planes. So in reality, it sounds really complicated, but you shouldn't believe everything you hear online, because it isn't. It's not complicated at all. So here's an example of a system with a solution. So you might be wondering, what is the solution of a system of linear equations in three variables, and what does it look like? Well, a solution is simply any triplet, ordered triplet, x, y, z number. So a point, any point that's on all three planes at the same time. So mathematically, we say that that point satisfies all three of the equations. This specific system here has the solution -1, 2, and -2. That's the point that's on all three of those lines at the same time. Let's talk about possible solution categories. So just like in linear systems of two variables, we have three options for our solution types. We have the first option, which is only one solution, where you can see the solution, which is a point in three space, is here. The yellow dots here you see in the top, called the top graph and then the bottom graph. So if you just have one point, then that point is your solution. Another option is you could not have any solutions, and you can see both of these pictures. You don't have a single point that's on all three planes at the same time. The second picture here, these two are parallel. The red and the purple plane are parallel, and they never touch. Down in the third picture, you've got all this area here where nothing ever touches, and everywhere else you just have two planes touching at the same time. So there's not a single spot that all three touch simultaneously. Your last option category is infinite solutions. So you can see here in the picture that all three planes touch in what appears to be a line. So any point on that infinite line would satisfy all three equations, therefore be on all three planes at the same time. So those are the three categories that we should be thinking about. So how do you know which option you have for the system you're in or you're given to solve? Well, you simply start solving the system. And if you get an answer, an x, y, z coordinate, then you know you are in option number one, which is one solution. If, as you are solving your system, your variables drop out, all the letters drop out, all you're left with is numbers and equal signs, then you're in either option 2 or option 3. If what you have left is a true statement, meaning 2 equals 2 or 0 equals 0, then you know you're in the infinite solutions option. If you're in option, otherwise you're in option number 2, which is the no solution. If what you have left makes a false statement, like 0 equals 2, then you know you have no solution. So that's pretty simple. How do we solve these types of systems? We choose 2 of the 3 equations we're given, and we use the substitution or addition method to eliminate one of the 3 variables. And then we repeat the process by choosing 2 different groupings of the 3 equations, and we eliminate the same variable. That gives us 2 new equations with just 2 variables, and then we're back to the world where we only have 2 equations and 2 variables, and we solve that system using substitution or addition. Once we've solved that system, then we take those 2 equations, substitute them back in, and find our third equation. Our third variable. All right, now we've had a quick overview. Let's actually solve a system. You've seen the big picture now, so let's solve a system. This system has only one solution, so we're going to go through and we're actually going to get an answer. If we were looking at this system, I would probably take first 1 and 2 and use them, because when we add them together, if we multiplied the second one by 2, then we could get rid of the y's. So let's do that. Let's take equation 1 plus 2 times equation 2. So the numbers that are circled, those are equation labels. So equation 1 plus 2 times equation 2. What do we get? So equation 1, well, what is equation 1 first of all? Equation 1 is x plus 2y minus 3z equals 9. So that's equation 1, right? That hasn't changed. Now we multiply 2 times equation 2, which gives us 4x minus 2y plus 4z equals negative 16. And that is, we'll call that 2.1 because it's equation 2, but it's been slightly changed. And now we add these two. What do we get? We get 5x. We get a 0, which is perfect because that's what we wanted, right? We wanted the y's to drop out. And we get a positive z equals negative 7. So we have a new equation here. 5x plus z equals negative 7. We're going to call that equation 4. So now let's go back and do 2 other equations to see if we can also drop out the y. So why don't we use equation 3 and then equation 2? Because if we multiply equation 2 by 3, then we can drop out the y's. So let's do that. Let's use equation 3 plus 3 times equation 2. So equation 3 is negative x plus 3y minus 4z equals 15. And again, this is equation 3. Now let's do 3 times equation 2. So that gives us 6x minus 3y plus 6z equals negative 24. And we'll call this 2.2 because it's not equation 2, it's something different. When we add these equations, what do we get? 5x plus 0 plus 2z equals negative 9. So we have a new equation here. 5x plus 2z equals negative 9. We'll call that equation 5. So now we've gone through the 2 groupings and we have eliminated the same variable y both times, and now we have 2 new equations, equation 4 and 5. So now we take equations 4 and equations 5 and we solve for the x and the z that's in there. So now we're just back to 2 equations, 2 unknowns. So we can use addition or substitution here. So let's use addition, and let's take equation 4 and subtract equation 5 from it. So it's just like multiplying by negative 1, multiplying equation 5 by negative 1 and then adding. So let's take equation 4, which is 5x plus z equals negative 7, and then negative equation 5, so that's negative 5x minus 2z equals positive 9. And this was equation 4, and this is a new equation 5, so we'll call that 5.1. When we add these, we get 0 minus z equals 2. So that gives us z. If we multiply both sides by negative 1, we get z equals negative 2. So that's nice. We've just found one of the variables. Now we can take z equals negative 2. It's a pretty shaky negative 2. And we can plug it into 4 or 5, whichever equation we want, and solve for x. So let's use equation number 4. So equation number 4 would be 5x plus z equals negative 7. So we know z is negative 2, so let's plug that in. So we have 5 minus 2 equals 7, negative 7. If we add both sides of the equation, add 2 to both sides of the equation, we get 5x equals negative 5. And then if we divide both sides by 5, then we get x equals negative 5 over 5 is negative 1. Awesome. Now we can take these two values that we know z equals negative 2 and x is negative 1, and we plug those into equation 1 or 2 from the beginning and solve for the remaining variable, which is the y. This is called the back substituting part. So let's use equation number 1. Equation number 1 is x plus 2 times y minus 3 times z equals 9. So again, this is equation number 1. We have, what do we have in here? We have an x. We know what the x is, right? We just solved for it. X is -1. And what else do we have? We have z. What is z? Z is -2. That's nice. What else do we have now? This gives us -1 plus 2y. A -3 times -2 gives us +6. So we have -1 plus 2y plus 6 equals 9. The 6 and the +1 give us +5. So we have 2y plus 5 equals +9. What else can we do now? We've got to solve for y, right? So our next step maybe should be subtract 5 from both sides. It gives us 2y. Well, that's a crazy looking y. 2y equals 9 minus 5 is 4. And then divide both sides by 2. And we get y equals 4 over 2, which is just 2. Awesome. Now we can take our 3 values. We have an x, which we know is -1. We have a y, which is 2. And we have a z, which is -2. And that's the solution. That's the point that is on all 3 of these planes at the same time. Thanks for watching. If you guys have questions, let me know.